now we're going to use our Hessian that we just talked about to do a second derivative test. And the test is just directly taken from the observations that we made in our examples. If we're at a critical point, and remember what that means is that the gradient is 0 or doesn't exist, but those are the first derivatives. Then we go past the first derivatives, we look at the second derivatives. There's a technical assumption. Technically, we're going to assume that those second derivatives are continuous near the point AB. But that's going to be true for every function you'll ever run into. Then, according to our observations, if the discriminant is positive and f(x)(x) is negative, then that point was a local maximum. If the discriminant is positive and f(x)(x) was positive, then the point AB is a local minimum. And finally, if the discriminant is 0, then that point is a saddle point. But I guess that wasn't final. What's really final is if the discriminant is 0, the test is inconclusive, and you just can't tell if it's a maximum or minimum based on the second derivative test. And you have to look at something else, such as a contour plot, perhaps. One little note here, in two spots here we say look at f(x)(x), and you might wonder, well, what about f(y)(y)? And the fact is that if the discriminant is positive, then those two entries have the same sign. They're either both plus or both minus. So you could look at either one of them. If f(y)(y) is positive or negative, then that means that f(x)(x) is also positive or negative. It's the same thing. So we stated it with f(x)(x), but it could have been the other way. All right, here's an example. f(x)(y) is 2x squared plus 7xy plus 5y squared. Let's try to find the maxima and minima of this function. So let's start by finding the derivatives, the first order partial derivatives. Fx is 4x plus 7y, and fy is 7x plus 10y. So the gradient of f is the vector 4x plus 7y, 7x plus 10y. So we'll set the gradient equal to 0 and get the equations 4x plus 7y equals 0, 7x plus 10y equals 0. All right, in order to solve these, we could use elimination or substitution. Let's use elimination. And you're welcome to pause the video and try solving it yourself using substitution if you want. But let's try using elimination. In order to make the numbers easier, let's multiply the first equation by 7. And let's multiply the second equation by 4. And then subtract them. And we'll get 0x plus 9y equals 0. And that tells us that y equals 0 in our solution. And at this point, let's stick in y equals 0. So we get 4x equals 0, or 7x equals 0. And that tells us that x also equals 0. So the critical point is xy equals 0, 0. And there's no points where this is undefined. This is defined and it exists. This gradient is defined and it exists for all x's and y's. So we don't have any of that type of critical point in this example. We only have the 0 type of critical point, which is the origin, xy equals 0, 0. Okay, so that's our only critical point. Now, is it a minimum or a maximum or a saddle point? In order to answer that question, let's look at the Hessian. So we already have our first derivatives written up here on the page. We can use that to find the second derivatives. Fxx is 4, fxy, so I'm taking my fx, my partial with respect to x, and differentiating that with respect to y, we get 7. And fyy, the second derivative with respect to y, we already have one derivative with respect to y, and we differentiate again and get 10. So that means that the Hessian matrix is 4, 7, 7, 10. We only have to figure out the 7 ones, and then we can copy it to the other side of the matrix. And not for this example, but if there had been x's and y's in there, then we would have plugged in our 0, 0. With that, we can figure out the discriminant. The discriminant is, all right, 4 times 10 is 40, and we're subtracting 7 times 7, 49. We get minus 9. That's less than 0. Do you remember what it means when the discriminant is less than 0? Well, you might not have the second derivative test memorized yet. Let's go back and look. If the discriminant was less than 0, then that point is a saddle point. So in this case, point 0, 0 is a saddle point. And in terms of our original function, to get back to the original question, which was find all the maxima and minima of this function, well, there aren't any. This function f has no local max or min. And that's the answer.